Section 3.4, Energy and Work. So energy and matter make up everything that we see. They make up all of the universe. You have stuff and you have stuff moving. And that stuff moving has energy. And sometimes that stuff just being there has energy. It all relates down to forces, things like gravity and electromagnetism and electric forces. Matter is essentially the stuff, and energy is the stuff that moves the stuff. So everything we see has some amount of energy associated with it. You really can't have any object that has zero energy associated with it. One of those things that Einstein did was kind of show that if you have mass, you have some energy. That is part of that E equals mc squared thing. Now, by definition, in physics, we refer to energy as the property of a system that allows it to do some type of work. And work in physics has a particular meaning. Work means that you apply a force to something, and that object moves some distance. The force and the distance that the object moves has to be in the same direction. Otherwise, the force isn't doing the work. So, energy allows something to do work. So energy allows something to apply a force to something and move it some particular distance. So work, we can measure. We can measure the amount of force on something, and we can measure how far it travels. And when we do that, we say that work is proportional to the force that something travels times the distance that it travels. If you apply a greater force to something, you do more work. If you move something a greater distance, you've done more work, even using the same force. Work is measured by combining the units of force, which is measured in newtons, with the units of distance, which is measured in meters, so that we get units of what is newtons times meters, but in general we call it joules. 1 joule of work is done whenever you apply a force of 1 newton and it causes an object to move 1 meter. When we have much larger values of work, we use metric prefixes so that we have kilojoules, which is 1,000 joules, or megajoules, which is 1,000,000 joules. Things on the order of kilojoules are things that you do every day as you move objects and do things like that. That's going to be around the general measurement of a kilojoule. Smaller things, some electrical appliances, electricity, will run on joules or less, or sometimes even less than that. Household appliances, probably somewhere in the kilojoules area. When you think about doing work, when you think about working hard, or whether you worked hard one day and didn't another day, you think about how much it physically expends you to actually do work. So you think of work as being a physical expenditure. But work in general doesn't really measure that so much. It measures what you have to do to complete that physical expenditure. What you are generally thinking of when you think of the physical act of working is more a measurement of what's known as power. Power is a measurement of how much work is done over the amount of time that it takes. So what that means is that if you do the same amount of work in less time, then you've used more power. If you do the same amount of work in a longer amount of time, then you use less power. So if you have to, say, clean a room or something like that, if you do it very quickly, you're going to use a lot more power. Well, you worked hard. Whereas if you do it very slowly, you use less power, but you didn't work as hard, but you still got the same amount of work done. It's very similar to if you think about carrying things up a flight of stairs. If you carry it up a flight of stairs very quickly, it's going to take a lot of work, right? It's going to take a lot of power. But it's the same amount of work physically for you to carry it up the stairs slower. You just use less power. Power can be thought of as the rate at which some amount of energy is changed into another type of energy. And so power is a rate. It's measured in units of energy per amount of time, so joules per second. But joules per second has a particular name. We call that watts. And 1 watt of power is what you use to do 1 joule of work for 1 second. So let's go back to the example of carrying a bag of groceries or something up a flight of stairs. When you do that, you have to do some amount of work and use some amount of power to do that. But as we saw, power is just a measure of how we change the energy of an object from one form to another. So what energy is changing whenever you carry something up a flight of stairs? When you carry something up a flight of stairs, you're changing its position relative to the surface of the earth, right? So if you were to drop something from a higher place, from the top of the stairs, it would fall much farther, and thus it would accelerate, and it'd be traveling much faster when it hit the ground, as compared to if you dropped it from the bottom of the stairs. What you've done is you've changed that object's position relative to the earth. You've given that object what we call potential energy. More potential energy because it's further from the earth. It has more potential to fall and strike the earth. More potential to gain energy or gain momentum and speed up. Some objects have some amount of energy based on their position, right? Things that are way up high off the ground, if they were to fall, would have a lot more energy when they hit the ground than something much closer to the ground. Also, things like rubber bands, springs, if you stretch them, they snap back. Right? If you compress a spring, it pushes outwards. They bend back to the original shape. Elastic objects do this too, or any type of elastic object does this. This is a type of potential energy. When you compress it, it wants to push out. It wants to snap back into place. You can also find potential energy within chemical reactions. But when we lift something up a flight of stairs, we have to do work to lift something up against the force of gravity. And if it's elevated from the ground, it has more potential to speed up as it hits the ground. And so we call this type of potential energy gravitational potential energy. If we release the object, it'll fall and it'll accelerate to the ground. It'll speed up. It'll experience a greater change in momentum by experiencing a force over a longer period of time. The amount of potential energy that an object has in terms of its position from the surface of the earth, we can directly measure. It's its weight based on its height from the ground. Its mass times the acceleration due to gravity, which is the weight, the force that the object would experience, times the height, times the distance that it would have to fall, times the distance that it would travel with respect to how high up it is from the ground. So we have a force times the distance. We have work. Work is done to change the potential energy when something falls. Now we can use height as any particular reference point. So 1 meter difference from the floor to to a tabletop, and from the tabletop to an object, the object's going to have the same amount of potential energy for that 1 meter, regardless of where that 1 meter is. If you drop it to the tabletop, it's going to speed up for 1 meter. If you drop it from the tabletop to the ground, it's going to speed up for 1 meter. Those two amounts are equal. Gravitational potential energy is how roller coasters work. When you get on a roller coaster, you go up to the top of a hill, they lift you with a chain, and then at that point you're released. And you go down, and you speed up as you go down, and then that energy that you gain as you speed up is then used to send you through some loops and things like that. And then you go back up through another hill where you go up to the top and then drop back down. Sometimes that second hill will have a chain, sometimes it won't. Usually it has a chain to stabilize you, if nothing else. So gravitational potential energy is the reason that roller coasters work. Now, continuing with the roller coaster example, when you reach the top of the roller coaster, you have a lot of gravitational potential energy. As you start to go down, you speed up, you get faster and faster. Your potential energy changes into another type of energy, which is known as kinetic energy. Kinetic energy is the energy of motion. It's the energy of things moving. Objects that have kinetic energy are capable of doing work. Moving objects, if they hit something, can do work to that object. They can apply force and cause it to move some amount of distance. The energy of motion we call kinetic energy, and we can measure that as 1/2, so the number 0.5, or however you want to think about it, times the mass of that particular object, times its velocity squared, how fast it's traveling squared. The direction here does not matter. Potential and kinetic energy are scalars. Doesn't matter which direction they're traveling. All that matters is that you know the amount of energy that it has. Similarly, if you have some amount of kinetic energy of an object and you want to stop that object, you have to do some amount of work to stop the moving object. You have to do some amount of work to change the kinetic energy of that object. Also, the amount of kinetic energy that you'd have to use, or the amount of work that you'd have to do, is equal to the speed squared, which means that if something is going twice as fast, it's going to require 4 times as much work to stop it. If it's going 4 times as fast, it'll require 16 times as much work to stop it. So work and energy here are clearly related, and there's a reason for that, and you're going to see that. When you do work, energy changes. When energy changes, work is done. The two are inherently linked.